So, lecture 4, the topics for to be covered are the following. As always, we will do a quick summary of what we have done in the last class, but with a little additional information so that it is not just a repetition, some additional perspectives. Today's lecture, we will look at the process of reconstruction. In terms of the last time we talked about the filter that we use for reconstruction. So, today we will talk about the process of reconstruction. Then from an ideal reconstruction filter, how do we work our way towards a realizable reconstruction filter. So, it is a two-stage process by which we get the realizable filter. And we will be talking several times about discrete time processing of continuous time signals. So, multiple times we will visit this concept, because I want you to feel very comfortable about going from continuous time to the discrete time, where the discrete time sampling is different. So, basically, in order to get a good understanding of the multi-rate systems, we keep referring back to the continuous time, and this is a very good example of what we could do. The relationships between continuous time and discrete time in the frequency domain, what happens when you go, when you do the process of sampling, when you do the reconstruction. This is a very, very important framework that is covered in today's lecture. We will also talk about some aspects of how do we develop a reconstruction process, what happens in a D2A, for example, if that for an understanding. What we are assuming is that all the students are familiar with what contents of Oppenheim and Schaefer chapter 2. Primarily that would be the definitions of discrete time signals and systems, understanding of LTI, the discrete time Fourier transform and its properties, and basic operations. We will just refer to some of them in passing in today's lecture. That is our underlying framework. Our focus primarily is on Oppenheim and Schaefer chapter 4 for the time being. Written assignment number 1 and computer assignment number 1 both will be uploaded in a few hours time. Please do take time to look at it and get started. The Tuesday hour is for doubt clearing. It is not an official lecture, but that is a time that the TAs and I will be available to answer any doubts. Okay, so just to pick up where we left off, we said in the last class, we made this statement that if we wanted to look at a continuous time signal sampled at omega s, we will get a band limited signal when we do the reconstruction process. It will be limited to omega s by 2, from minus omega s by 2 to omega s by 2. The ideal reconstruction filter is one that will get rid of the images. Notice that the images will be located at multiples of omega s. This goes from minus omega s by 2 omega s by 2 and is 0 everywhere else. So, it basically removes all other images except the k equal to 0 version of the primary image. Now, the other aspect is the scaling. So, keep in mind that there is a scaling element which is part, and I sure you would have been able to verify that the corresponding impulse response of an ideal reconstruction filter is obtained, is basically a sinc function. Okay, we will come back to looking at it in a little bit more detail, but let us just summarize or recap all the key results that we have said so far. So, the sampling process xs of j omega, the spectrum of the sampled signal, we said has a scale factor 1 over Ts summation k equal to minus infinity to infinity xc of j omega minus k omega s. Again, this is more so that you are very familiar and comfortable with the expression. Okay, the scaling factor, the multiple. So, k equal to 0 is your underlying continuous time spectrum. Multiples of k plus minus 1 plus minus 2, you get all the shifted versions, and those are the images that occur during sampling. Those are the ones that you need to remove when you do the reconstruction process. Okay. The relationship between the continuous time signal and the sampling frequency, omega s sampling frequency is equal to 2 pi by Ts. And very important relationship, as you reduce Ts, that means your sampling period is reducing, sampling frequency is increasing. So, that is a very important relationship. I suppose it is obvious from the fact that omega s is equal to 2 pi by Ts that they are inversely related. What is more important is the corresponding frequency domain interpretation, which I would like you to keep in mind. So, basically if I have a signal that has got a from minus omega naught to omega naught, it is a band limited signal. I sample it at some omega s that satisfies Nyquist frequency, Nyquist criterion omega s. So, there is no overlap of the spectra, and now if I specify Ts dash is equal to Ts by 1.5, just for interest, just to see what happens. So, this basically means that my corresponding sampling frequency, I have reduced my sampling period. So, increase my sampling frequency by 1.5 omega s, the original. So, the new version that we will get as in terms of the spectral representation, the original spectrum minus omega naught to omega naught. So, now instead of omega s, it will go to 1.5 times omega s. So, basically the spectrum, the copies of the spectrum now become shifted apart. So, this is omega s dash, that is equal to 1.5 times omega s. Okay. So, this is the underlying process, again being able to quickly relate to what is happening in the time domain to what is happening in the frequency domain, very important. Now, in the last lecture we did some amount of discussion on the sampling of sinusoids. Okay, sampling of sinusoids, we looked at a case where there was no aliasing and we did a reconstruction. We looked at the case where there was aliasing and also looked at the reconstruction. So, the statement that we can make as far as the sampling of sinusoids is concerned and the reconstruction is that the reconstructed signal depends on the spectrum that lies between minus omega s by 2 to omega s by 2. It does not matter whether that was part of the original spectrum or of one of the shifted spectra. That is what we saw in the last lecture. So, depends on the signal in the range minus omega s by 2 to omega s by 2. In the case of sinusoids with the aliasing, we found that what lies within the spectrum is also a sinusoid, but of a different frequency. So, that was the observation. Okay. Now, in terms of the ideal reconstruction filter, we had looked at this information, so we will not repeat that. Now, let me just sort of mention the key observation from the example that we looked at, that was the example of generating CD data, compact disc. Generating CD data, I will not redraw the figure, I am sure you can refer to it. The key principles that we said was we were doing 4x oversampling. Okay, so 4x oversampling was the strategy. So, the sampling frequency instead of 44.1 went to 176.4 kilohertz. Okay. Now, the reason for doing that, because we had an analog anti-aliasing filter. Anti-aliasing filter really was not an anti-aliasing filter because it allowed aliasing to occur. This was actually turned out to be a low pass filter with very relaxed criteria. The cutoff frequency, as we mentioned in the last class, cutoff frequency was actually not omega s by 2, but something well beyond omega s by 2. In fact, we said you could go as high as 156 kilohertz. Okay. Now, that is interesting. I hope you have had a chance to look at that and sort of feel comfortable with it, that this is a analog filter that will allow aliasing to occur as part of the sampling process, does not affect us in the final result, because there is a digital filter that follows. There is a digital low pass filter, that is after sampling, digital low pass filter. What was the stop band cutoff for this digital low pass filter? It was in terms of actual frequency, it will be 44.1 divided by 2. So, this should be 22.05 kilohertz. Okay. But digital frequency, when you represent it in terms of the discrete time filter, there is no kilohertz notation, right? It has to be only radians. So, how do I convert it to radians? My sampling frequency is 176.4 kilohertz, that corresponds to 2 pi, right? That is my sampling frequency. So, now the question is, if I have 22.05 kilohertz, what does that correspond to? Pi by 4, okay, pi by 4. So, this is a low pass filter. The digital filter is a low pass filter with cutoff pi by 4 minus pi by 4, okay. That is if you could design an ideal low pass filter, but we are basically, remember, this is a practical system. So, do I design a low pass filter that looks like this, or do I design a low pass filter that looks like this? Which one is the one that I am allowed to do? So, if I want to strictly satisfy the anti-aliasing property, I have to go with the orange one. That is the desired, or the desired low pass filter, that digital low pass filter. Remember, pi by 4 corresponds to 22.05. If anything outside of that is allowed, then I will run into problems with the effect of aliasing, because there is some unwanted signals that are present, because my analog filter allowed things to creep in. Okay, now having designed a low pass filter which looks like this, practical low pass filter. So, the edge, this is 20 kilohertz, you have to transfer to discrete time, discrete frequencies. This corresponds to pi by 4, that is the filter that we use, and the last step that we did after the digital filtering was downsample by a factor of 4, downsample by 4x. Okay. So, the combination of the analog low pass filter plus the digital low pass filter, effectively this was my anti-aliasing filter. Okay, this is my anti-aliasing filter. The advantage that I have gained through this mechanism is that the complexity of the analog filter was shifted over to the discrete time domain, so that the digital filter could be the sharp filter, and effectively the aliasing is not present in the signal band of interest. Okay. So, again, this is an example, but it sort of highlights the important results that we want to emphasize. Okay. We also need to make sure that we are formally stating the relationships. So, let me just mention that very quickly before we move on to the rest of the lecture. So, the discrete time relationship, if I have a sequence, discrete time sequence x of n, I talk about a discrete time Fourier transform which is x e of j omega, and the relationships x e of j omega is continuous in omega, periodic with period 2 pi, summation n equal to minus infinity to infinity x of n e power minus j omega n. Okay, and x of n can be obtained by the inverse transform 1 by 2 pi integral minus pi to pi, because anything outside of a minus pi to pi range is a repetition, x e of j omega e power j omega n d omega. Again, this is something that you are familiar with, but I needed to write it down so that we are comfortable with what is the basic definitions. And very often in DSP we do not really worry too much about what happened in the continuous time, but we need to be fully aware, because we are going to be going back and forth. So, the underlying continuous time signal, so if it is x c of t with the Fourier transform x c of j omega, let me just write that down for completeness. X c of j omega is an infinite integral minus infinity to infinity x c of t e power minus j omega t dt. Again you can see close similarities. The inverse transform in this case also turns out to be an infinite integral. It is 1 by 2 pi minus infinity to infinity x c of j omega e power j omega t d omega. Okay, so that more or less sets the framework of what we are trying to do. Then what is left is the link between the continuous time and the discrete time. Remember the link that goes back and forth, in one way it is sampling, the other way is the reconstruction process. So the discrete time frequency omega is related to the continuous time frequency through the sampling period Ts. Ts is 2 pi divided by omega s. So basically any frequency omega continuous time can be mapped to the corresponding discrete time frequency using this following 2 pi by omega s or 2 pi times omega by omega s. Okay, it's as if you took the continuous time frequency, normalized it by omega s and then mapped it in the range 0 to 2 pi, omega s equals to 2 pi. So again this is a useful relationship, simple one, but it helps us be able to map from one domain to the other. Now comes an important, it is more of an observation. So omega s is the sampling frequency, that is the frequency with which the spectrum repeats. Now in the discrete time this corresponds to 2 pi. So 2 pi in the discrete time, I will just put it as discrete time, this is continuous time. So the frequencies 2 pi maps to omega s. Okay, and very often we are interested in omega s by 2, because that is the portion of the spectrum that will get reconstructed. So that means anything from minus what will in the discrete time representation, that is of interest. Okay. So typically the reconstruction process is in the range minus omega s by 2 to omega s by 2. This would correspond to, in the discrete domain, this would correspond to minus pi to pi. Okay, basically looking at one period of the discrete time Fourier transform, the spectral properties. Okay. Another sort of related observation, now when I go from 0 to 2 pi, where does my highest frequency occur in the discrete, when I am looking at the discrete time representation? It occurs at pi. So basically an observation that we would note down here, maybe to the side, is that the pi corresponds to the highest frequency, which basically also says 2 pi will wrap around to DC. Okay. So again that is just by way of all the different relationships that we have. Okay. So I think we are now ready to take on in our discussion, that is the process of reconstruction. Again it is a subject that you would have studied in basic DSP, but our interest is to certain observations, because we will be looking at it multiple times in the context of multi-rate system. So the process of reconstruction. So the basic underlying system is that I have a sequence x of n, I must reconstruct it into a continuous time signal xr of t, and the steps that we would need to take. The first step is going to be that I need to go from the discrete domain, where I am representing in terms of numbers, a sequence of numbers, to something in the continuous time. So from a sequence we need to convert it into an impulse train, Okay. Then once you have it in the form of an impulse train, then it is a continuous time signal, let us call it as xs of t. Then this one has to be will be reconstructed by removing the unwanted portions of the spectrum. So this is going to be the reconstruction filter, and for the moment we are going to assume that it is ideal. We will remove the ideal assumptions very shortly, but for now we will assume that this has a spectrum HR of j omega, and then based on that we produce an output which is the reconstructed time domain signal. Okay. So, the inputs that we need to give, one is a reference point which tells what is the spacing between that. So, there is a underlying Ts that needs to be specified when I do the reconstruction process, because otherwise these are just samples. I could interpret them as 1 millisecond spacing, or I could interpret them as 100 milliseconds between them. So, we need to specify at what sampling period we are going to do the reconstruction. So, writing it mathematically gives us the best insight. So, let us write down the process that we have written down. So, xs of t, the impulses. So, it takes the sampled values x of n and generates the corresponding Dirac deltas t minus nts. Notice that the Ts sampling period has come into play, and the shift of the delta function base depends on the sequence number, and this is n equal to minus infinity to infinity. So, and the next step, which is the reconstruction step, xr of t, if this is xs of t and this can be related to an impulse response hr of t, it is an LTI system. So, there is an impulse response. So, xr of t will be xs of t convolved with hr of t, very Fourier transform relationship. Basically, I am looking at the input output of an LTI system, the impulse response convolved with the input gives me my output. So, if you write down the expression now, we get a very interesting result. So, it is summation n equal to minus infinity to infinity x of n delta of t minus nts, this function convolved with hr of t, hr of t. Okay. Now, I would like to invoke a result that I am sure you are familiar with in the continuous time and in the discrete time, but the continuous time property basically says that if I have a delta function which is which occurs at a value nts, and I convolve this with hr of t, what do I get? Basically, the impulse response will shift with the center will shift to where the impulse occurs. So, hr of t minus nts. Okay, so, that is a result that is known when I convolve anything with an impulse function. Basically, the function is preserved, but it is only shifted to where the function occurs. So, this then tells me that the reconstructed signal can be very nicely expressed as n equal to minus infinity to infinity x of n times hr of t minus nts. And this is a I am sure this is not a new equation, but I want you to sort of look at it with a fresh pair of eyes. So, basically what we are saying is that the reconstruction has got a certain impulse response, and we showed that the ideal impulse response is a sinc function. Now, once we get to the point where we have written the reconstructed signal as shifted versions of the reconstruction filter impulse response, but each one appropriately scaled by the sample value. Okay. So, now here is the visualization. I need to look at it. Basically, if I were to sketch the hr of t, ideal reconstruction filter, it is a sinc function. It has 0 crossings at Ts, 2Ts, 3Ts, 4Ts and so on, and in between the ringing function. Okay. So, I have sort of shown you what it should look like. This is what this is expanded view, just to give you a feel for it. But basically, the important thing is to look at the response of the impulse of the reconstruction filter. Now comes the reconstruction process. So, if I have which is the sample at time t equal to 0. I have to produce a copy of the reconstruction filter, which is the red version. So, that is the reconstruction filter centered at t equal to 0. Then at t equal to 1, it is the blue copy of the reconstruction filter, and then at t equal to -1 is the green copy. So, you have the green copy sort of occurring, the reconstruction filter, the red version, the blue version. Notice at the sampling points, all of them. So, that is the very, very important property, because what that tells us is when the resultant signal will have the same value as the sample points. Those sample values will not be altered, everything in get filled in, but the sample values will not be altered. And how do I show that? So, basically the purple one is the sum of all these signals. So, basically it is these is sum of whatever, take all these signals that are falling in the certain window, and you will find that at the sampling points you are exactly coinciding sample value x of n, and then at all the other points signal. So, the ability to visualize the reconstruction process in this manner is very, very important. And what happens in terms of the process, and why is the Nyquist property so important? Why is it that we have to worry so much about these zero crossings? Because if these zero crossings were not satisfied, then the original sample values would have gotten altered. So, that is the reason why. So, this is one of the important criteria that we will use, or we would like to have in any, that the impulse response goes through zero crossings at Ts, 2 Ts, 3 Ts, and that is sometimes referred to as the Nyquist property. Again, we use the word Nyquist so many times in this particular discussion. This is a Nyquist filter, or a filter that has this Nyquist property in the time domain. Okay, another result, maybe we write it in the place where we have written all the equations that we would need to, and this is the introduction of the frequency domain elements in our discussion. So far this is the time domain version of it. The continuous time signal x e of j omega reconstructed to form a continuous time signal, right? And in the process we went from the discrete time omega to the continuous time omega, and then passing through the reconstruction process. Since we know that omega is related to omega times Ts, we can also say that yes, omega is just a variable, whether it is the discrete time omega or the continuous time omega. So, I can very well write this x e of j omega as x e of j omega Ts. Am I right? Because that is the relationship between the continuous time omega and the discrete time omega. Now, this is very important, because this is a function which is periodic in omega with period 2 pi. Okay, this is the discrete or the normalized frequency. Now, this happens to be a function that is periodic in omega. I have just mapped it. So, with period equal to 2 pi by Ts, 2 pi by Ts. Okay. So, the resultant, the reason for this particular expression is as follows: xr of j omega, the reconstructed signals spectrum, is the spectrum of the reconstruction filter Hr of j multiplied by the continuous time representation of the spectrum of x of n. Am I right? Basically the spectrum of the signal at this point, and that I can if there is no loss of information going from x of n to xs of t, then I can write this as x of e of j omega Ts. Okay. Now, we will come back to looking at this expression a little bit more, because this is a very, very key result, because what it is saying is there is a continuous time spectrum which has got lots of replicas. Where did the spectrum come from? It came from the discrete time signal also got different spectra. So, what did I do? I took the discrete time spectrum, spectrum represent, and then I chopped off everything with outside a certain window, and the outside of the window that is specified by the reconstruction filter. So, this equation is a key equation, and we will come back to looking at this multiple times in our discussion. Okay, so the reconstruction filter is a sinc function, or it has got a the Nyquist property. It does not have to, you can use other reconstruction filters as well, but this property is very important, so that you do not change the values at the sampling points. Okay, and this is the reconstruction process. It basically it turns out to be a superposition of the several repetitions of the reconstruction filter impulse response with the appropriate scaling that is very important for us.